to the lecture 12 in the series on noise control in mechanical systems. Today we will solve some problems with respect to sound radiation that we have studied in the previous two lectures. Okay? So, that is the outline. So, we will study about radiation, acoustical sources, sound fields and flexural waves we have studied, and their numerical problems we will be solving. So, let us see the problem 1. Suppose we have a large room and we have got a boxed speaker. It is generating 0.8 pascals amplitude of sound wave at 100 hertz frequency at a particular reference point P in the room. Now, so these kind of speakers we have brought from the market. Now, we want to arrange them. So, we want to have different arrangement of the speakers. So, let us say in the first arrangement, two such box speakers, they are added antiphase at a separation distance of 50 centimeter, whereas in the second one, same two box speakers added in phase at a separation distance of 50 centimeters. Now, you have to find out what is the acoustic pressure amplitude radiated by the above two arrangements. So, let us see here. So, if you think here the very first case, boxed speaker behaves like an acoustic monopole, and considering assumption that the room is much larger than the speaker dimensions, it is given a very large room. So, we can say that it is a free field propagation. So, here what we can say that typically when no other conditions are given, we assume that it is a free field propagation at the point P, at the reference point P. So, which means that spherical wave front is emitted, okay, and it is behaving like an acoustic monopole. Now, let us start and see what happens in arrangement 1. Two speakers or two monopoles antiphase at a distance of 50 centimeters. So, what does it behave like? It behaves like a dipole. This becomes a dipole. Okay. So, it behaves like a dipole, and in that case obviously if you have studied the previous lectures, the radiation efficiency of a dipole is less compared to a monopole. So, probably the acoustic pressure should go down. Okay, the same speaker should radiate not as efficiently as the case of a single speaker when they are in antiphase. So, let us see what would that be. Let us find out the radiation efficiency of this dipole with respect to the monopole. So, eta d by m should be WD by Wm, which is given as k square L1 square by 3. This is what has been found in the previous lectures. So, which means the energy radiated by arrangement 1 with respect to the energy of a single speaker is given by this. Okay. So, let us find out what this is. K. So, here we have got the frequency is 100 hertz if you think, okay, and therefore, K becomes omega by C, which becomes 2 pi into 100, and if nothing is given, we take it is an air at the room temperature and we take its corresponding speed of sound, and when you solve this, what you will get is 1.8212 as radians per meter as your wave number K, and L1 is 50 centimeters. So, let us see. Now, let us put all the values in SI units. So, centimeters we convert to meters. So, we get 0.5 meters whole square by 3. If you solve, you find this as the relative radiation efficiency. So, what it means is that the energy for arrangement 1 by the E naught of a single speaker is this thing. And we know that, so this means the intensity of the arrangement 1 by the reference arrangement, which is a single speaker, is the same thing here, and intensity is directly proportional to p square. So, this means that p square of arrangement 1 by p square naught is this quantity here. So, the acoustic pressure due to arrangement 1 should be square root of this, the ratio of this should be square root of their intensity or energy ratio, which comes out to be this thing here. So, what would be the acoustic pressure? That is has been asked here. Acoustic pressure due to arrangement 1 at the same reference point P is given by into P naught, and P naught here was 0.8. So, this comes out to be, if you solve it, 0.42 pascals. So, this becomes our answer for the first thing which we are supposed to find. Okay. Now, let us solve for arrangement 2. Okay. Again, arrangement 2 is in phase. So, here now it will not act as a dipole, but rather you can say extended monopole that are separated by 50 centimeter. Now, given that the room is very large, let us first see how does this 50 centimeter stand in terms of the wavelength. So, the wavelength of the sound is C by F. So, 345 by 100 hertz. So, it is 3.45 meters. So, you see here that this separation distance d is very small compared to the wavelength. So, now overall at a faraway point P, we can assume it equivalent to a bigger sound source, which is a, because they are in phase, so they behave like a bigger ball of mass pulsating, and they are creating the sound waves, and following the principle, each of them is individually generating sound waves that are in phase. So, the in phase sounds, so overall the pressure at point P should be P due to the speaker 1. So, P naught due to speaker 1 and P naught due to speaker 2, individual speakers. So, this becomes our pressure for arrangement 2. Okay. So, we are simply, it's a superposition of these two wave fronts coming from the two speakers. So, here simply it is 0.8 plus 0.8. So, the acoustic pressure which is asked due to arrangement 2 at point P is 1.6 pascals, just double of what would be there. Fine. So, I think that would be it. The acoustic pressure amplitude was asked for the two arrangements. Okay. Let us go and see problem 2. Now, in this problem what is asked, we have a 5 centimeter. So, let us underline and see what are the values that is given to us. A 5 centimeter thick steel plate vibrating such that we have a flexural wave in the steel plate, 200 hertz frequency. The density per unit area or the rho s is given as 400 kgs per meter square for that plate. The Young's modulus is given to us, Poisson's ratio is given to us. First of all, we have to find out the phase speed of the flexural wave that is created. Then answer the question that at this condition does the plate radiate sound, and if so or if so not, and then also answer what frequency of the flexural wave will give you the maximum radiation efficiency. So, let us attempt this. So, over here the things that are, this is the bending wave speed. The bending wave speed is given as Cb is equal to, over here what we have is, it is equal to omega square b by rho s whole to the power 1 by 4. Okay. Now, let us find these individual quantities. Omega should be 2 pi f, which is for a 200 hertz wave. Yeah. This comes out to be 1256.6 radians per second. Okay. The bending speed is given as E h cube by 12 times 1 minus. Okay, here I will use a different symbol for Poisson's ratio to not confuse it with the frequency. So, let us use this symbol here, this is for the Poisson's ratio. So, here all these values are given. The Young's modulus is given to be 200 gigapascals, okay, and Poisson's ratio is 0.3. So, 200 gigapascals into the thickness of the plate, which is 5 centimeter, converted into SI units, it becomes 0.05 whole cube divided by 12 into 1 minus 0.3 whole square. If you solve this entire thing, hopefully you should get this answer. Okay, as the bending stiffness in the SI unit. So, let us find out what is the Cb for these conditions. So, Cb at 200 hertz, let us find out. It is given as, you put all these variables in this equation. Rho s is given to be 400 in the SI units. Okay. So, on solving, what you get is, the answer is probably this one. Its speed, it is in meters per second. So, that is what was asked. What is the speed of the flexural wave? This is the speed of the, or the phase speed of the flexural wave that is generated in the flat plate under the given conditions. Now, will this plate radiate sound under the given conditions? So, what is the phase speed here? 308, and considering that the plate is surrounded by the air medium at room temperature, which is the most common medium. So, if nothing is given, we say that the plate is surrounded by air. So, here for the medium, the C is 345 meters per second for air at room temperature. So, this is the condition where C is greater than Cb. Okay. So, when C is greater than Cb, what is happening? We are, so Cb has still not reached the critical frequency range. So, this is below the critical frequency. This corresponds to below the critical frequency regime. Therefore, no radiation from the plate under these conditions. Now, let us see what frequency will get maximum radiation efficiency. Well, you know that whenever C becomes equals to Cb or F becomes equals to the critical frequency, at that region we get maximum radiation efficiency. So, for this particular plate, Fc is by this formula. If you solve, Fc comes out to be so let us put and find out. This is 345 whole square by 2 pi okay. So, once you solve all of that, hopefully what you should get is approximately 250 hertz, 250.4 hertz to be exact. So, here when the frequency is 250 hertz, then you will reach the maximum radiation, and as you can see, you can cross check that initially the given condition was 200 hertz, which was below the critical frequency, and hence there was no radiation at 200 hertz. Okay, fine. So, let us solve the problem 3. Now, here what we have is that we have a cube shaped machinery. Okay, we have got a cube shaped machinery. Side length is 10 centimeters. So, the dimensions are 10 centimeter, create sound waves at 150 hertz at the center of a reflecting factory room of dimensions given by 10 by 20 by 10 meters. Find the following. First of all, what should be the radiation type from this machinery, and then what you find out what is the extent of the near field, the far field and the reverberant field in this machinery. So, over here this represents very much our case which we have studied in the previous lecture. That is the case. You have certain machinery which is placed somewhere in the center of the room, and the room is pretty large compared to the dimensions of the machinery. So, the first thing is that this is 10 centimeter and the dimensions are where we are trying to measure are all in meters, so much. So, these and the wavelength, let us see what is the wavelength corresponding to 150 hertz. So, the wavelength lambda is 345 by the frequency 150, which is approximately 2.3 meters. So, you see that the small d, which is it is a 10 centimeters, so it would be 0.1, it is centimeters, which is much smaller than lambda. So, the source behaves as a point source or a monopole. Okay. So, the source is behaving as a monopole. So, in the free field it should be propagating spherical wave front. So, to answer what is the radiation type, we will say that in the large room in free field zone we have spherical radiation, and near field is always complicated. So, we do not deal with it, and then when it reaches in the free field spherical radiation. So, free field zone is when it is away from the walls, but near the walls. So, we will say that when the distance is roughly in the same magnitude as lambda. So, near the walls, so roughly within the same magnitudes within 2 meters from the walls, and ceiling and room, ceiling and floor, all of them are reflectors. It becomes a it becomes a reverberant. So, spherical radiation plus reflection. So, again it becomes a complicated field. So, does not stay spherical near the walls. So, we get a bit of a reverberant field or a diffuse field, okay, or otherwise when it is near. So, when it is away from the walls, so at least 2 meters away from any room surface, in that condition, in this particular condition you get a spherical radiation. Okay. Now, let us see what is the extent of near field, the extent of far field and the reverberant field. So, near field would be from the machinery source that is there to up to let us say up to 2 lambda, and the lambda here is 2.3 meters. So, up to 4.6 meters in all directions. Okay. Far field. So, far field also includes the reverberant field, by the way, because it can have reflections and not reflections. So, it would be, so suppose this is your machinery here, and let us consider the largest dimension, which is given to be 20. So, here it is 20. So, this distance here is 10 meters. So, the far field would be for largest dimension from 4.6 meters to up to 10 meters till the room surface, and for the smaller dimension, which is 10 meters, it would be from and 4.6 meters to up to, this would be 5 meters for the smaller dimension, considering the machinery is placed at the center. So, up to 5 meters, so very small. So, if you think of the room layout, let us take a top view of the room, and how does the near field and the far field zone look like. Suppose this is your machinery, let me draw a better layout, 10 by 20 layout. Okay. This is your 10 meters, this is your, sorry, this is your 20 meters, this is your 10 meters. Let us draw the zone for near and far field. Let me indicate the near field, this is the legend. So, near field with red and the far field with blue. And this is the top view. This is the top view of the room. And how does it look like? We have the machinery here. So, somewhere in the center we have this machinery. Okay. Now, what is happening is, let us draw the near field and the far field. So, up to 4.5 centimeter, 4.6 so roughly. So, let us draw a radius, a square 4.6 meters everywhere. So, that becomes our near field, and then we have the far field. Okay. And what is the extent of the reverberant field? Field close to the walls. So, in that same room, if I draw again that layout, this is the top view or layout of the room. Okay. So, and this is the small machinery source, then it should be roughly in the orders of magnitude of lambda away from all the surfaces. So, roughly 2 meters from everywhere. Okay. So, all of these are approximate dimensions. Okay. So, we will represent it using the green color. Let us use a different color for this reverberant field. So, the reason why I am drawing the reverberant field separately is because the reverberant and the far field, they are overlap. So, to make it more clear, this is your reverberant field. I can also show it here. So, here it is both far field and reverberant field. Far field as well. Okay, and this dimension here is 2 meters and so on. Okay, so with this, we just solved some numerical problems on this topic, and I would like to close this lecture. So, thank you for listening.